The situation involves a facility with a 440 kV 480/277 volt secondary transformer. Calculations indicate a secondary current of 662 amps, leading to the selection of a 700 amps breaker on the secondary side, based on transformer table 450.3b. A 350 horsepower motor is being added to this service. However, the preferred drive original equipment manufacturer only offers 300 horsepower and 500 horsepower drive options. The 500 horsepower drive, according to Electrical Code 430.128, requires a drive input rating of 697 amps multiplied by 1.15, equaling 802 amps, suggesting a minimum 1000 amps breaker. This results in a configuration where the transformer secondary breaker is rated at 700 amps, while the drive input breaker is 1000 amps. The transformer secondary breaker is rated at 700 amps, which is below the required 1000 amps minimum for the drive input breaker. This is not a desirable situation, as it could lead to nuisance tripping of the secondary breaker. Here are a few possible solutions to this issue. Firstly, increase the size of the secondary transformer. This would allow for the use of a larger secondary breaker, which could then accommodate the 1000 amps drive input breaker. This involves replacing the existing transformer with one that has a higher kV rating and consequently a higher secondary current capacity. The selection of the new transformer size should be based on a comprehensive load calculation that includes the 350 horsepower motor load, the existing facility loads, and any anticipated future loads. The load calculation should adhere to the guidelines outlined in the National Electrical Code. For motor loads, it's crucial to consider the motor's full load current, starting current, and any intermittent or continuous operation factors. The transformer's kilovolt ampere rating should be sufficient to supply the total calculated load without exceeding its rated capacity. The increased transformer size will allow for a larger secondary breaker to be installed. The appropriate breaker size is determined by the transformer's secondary current rating, typically sized at 125% of the transformer's rated secondary current, while adhering to the standard breaker sizes available. Secondly, use a different drive original equipment manufacturer. There may be other drive original equipment manufacturers that offer a 350 horsepower drive that does not require such a high input current. This option involves researching and comparing drive offerings from various manufacturers to identify a drive that meets the 350 horsepower requirement while having a lower input current demand. Consider factors such as the drive's efficiency, features, and compatibility with the existing motor and control system. Review the drive specifications, including the input voltage, input current, and any directing factors that may apply based on environmental conditions or altitude. Ensure that the selected drive complies with all applicable safety standards and certifications. Selecting a drive with a lower input current demand will reduce the required size of the drive input breaker, potentially allowing the existing 700 amps transformer secondary breaker to be adequate. Thirdly, use a variable frequency drive. Variable frequency drives can help to reduce the input current required by the motor, which could allow for the use of a smaller secondary breaker. Variable frequency drives control the speed of the motor by varying the frequency and voltage supplied to it. This allows for efficient operation at different speeds and loads, reducing energy consumption and minimizing the motor's inrush current during startup. During motor startup, a variable frequency drive gradually increases the voltage and frequency, limiting the inrush current and reducing stress in the electrical system. This can significantly reduce the peak current demand compared to a traditional across-the-line motor starter. By reducing the input current required by the motor, a variable frequency drive can allow for the use of a smaller drive input breaker, potentially resolving the mismatch with the existing 700 amps transformer secondary breaker. When selecting a variable frequency drive, consider factors such as the motor horsepower, voltage, current, and any specific application requirements. Ensure that the variable frequency drive is compatible with the motor and the control system, and that it complies with all applicable safety standards and certifications. Furthermore, it's crucial to review the National Electrical Code requirements for motor circuits, including the sizing of conductors, overcurrent protection devices, and disconnect switches. Article 430 of the National Electrical Code provides detailed guidance on these aspects. The motor's full load current, as listed in the motor nameplate, is used as the basis for calculating the conductor ampacity and the overcurrent protection device rating. Conductors supplying a single motor must have an ampacity of not less than 125% of the motor's full load current. This ensures that the conductors can safely carry the motor's current without overheating. Overcurrent protection devices, such as fuses or circuit breakers, are installed to protect the motor and the conductors from overloads and short circuits. The maximum rating or setting of the motor's overcurrent protection device is typically based on a percentage of the motor's full load current, as specified in the National Electrical Code. For example, inverse time circuit breakers are typically permitted to be rated at up to 250% of the motor's full load current, while dual element time delay fuses are permitted to be rated at up to 175% of the motor's full load current. Disconnect switches are used to isolate the motor from the power supply for maintenance or repair purposes. The disconnect switch must have an ampere rating not less than 115% of the motor's full load current. It should be readily accessible and capable of being locked in the open position. In addition to the motor circuit requirements, it's also essential to consider the transformer protection requirements outlined in the National Electrical Code. Article 450 provides detailed guidance on the overcurrent protection of transformers. Transformers must be protected against overloads and short circuits to prevent damage to the transformer and the electrical system. The overcurrent protection device for a transformer is typically located on the primary or secondary side of the transformer, depending on the transformer's voltage and impedance. The maximum rating or setting of the transformer's overcurrent protection device is based on the transformer's rated kilovolt-ampere in voltage, as well as the transformer's impedance. The National Electrical Code provides tables and guidelines for determining the appropriate overcurrent protection device rating for different types of transformers. It's crucial to coordinate the overcurrent protection devices for the transformer and the motor to ensure that the devices operate properly in the event of an overload or short circuit. Coordination studies are typically performed to analyze the fault currents and determine the appropriate settings for the overcurrent protection devices to minimize downtime and prevent damage to equipment. Ultimately, the best solution for the situation will depend on the specific circumstances and constraints of the facility. A thorough evaluation of the existing electrical system, the motor load requirements, and the available options is necessary to determine the most cost-effective and reliable solution. Consulting with a qualified electrical engineer or contractor is recommended to ensure that the selected solution complies with all applicable codes and standards. Additionally, consider the potential impact of the new motor load on the overall power quality of the electrical system. Large motor loads can cause voltage dips and harmonic distortion, which can affect the performance of other equipment connected to the system. Power quality studies may be necessary to assess the potential impact and implement mitigation measures such as harmonic filters or voltage regulators, if needed. Another consideration is the energy efficiency of the motor and the drive system. Selecting energy-efficient motors and drives can reduce energy consumption and lower operating costs over the long term. Incentives and rebates may be available from local utilities or government agencies to encourage the use of energy-efficient equipment. Furthermore, it's essential to implement a comprehensive maintenance program for the motor, the drive system, and the transformer. Regular inspections, testing, and maintenance can help to prevent equipment failures and ensure reliable operation. The maintenance program should include tasks such as lubricating motor bearings, cleaning cooling fans, tightening electrical connections, and testing overcurrent protection devices. Proper documentation of the electrical system is also crucial for troubleshooting and maintenance purposes. Accurate and up-to-date electrical drawings, equipment specifications, and maintenance records can help to identify potential problems and facilitate repairs. It is necessary to ensure that all electrical work is performed by qualified and licensed electricians in accordance with all applicable codes and standards. Electrical work can be dangerous, and improper installation or maintenance can lead to electrical shock, fire, or equipment damage. Finally, consider the long-term implications of the selected solution. Will the solution meet the facility's future needs, or will it need to be upgraded or replaced in a few years? Planning for future growth and expansion is essential to ensure that the electrical system can accommodate the facility's evolving requirements. When addressing the initial concern of the 700 amps transformer secondary breaker being insufficient for the 1000 amps drive-in per breaker, several strategies can be employed. Firstly, consider the actual load profile of the 350 horsepower motor. In many applications, motors do not continuously operate at their full rated horsepower. If the motor operates at a significantly lower load for extended periods, the actual current draw may be lower than the full load current specified on the motor nameplate. Conducting a load study using a power analyzer can provide valuable data on the motor's actual current consumption under various operating conditions. This data can then be used to determine if the existing 700 amps breaker is adequate for the actual load. Secondly, explore the possibility of using a soft starter instead of a variable frequency drive. Soft starters reduce the inrush current during motor startup by gradually increasing the voltage applied to the motor. This can significantly reduce the peak current demand in the transformer and the secondary breaker. Soft starters are typically less expensive than variable frequency drives and may be a suitable option if speed control is not required. Thirdly, consider using a current limiting fuse in the drive input circuit. Current limiting fuses can quickly interrupt high fault currents, protecting the drive and the transformer from damage. Selecting a current limiting fuse with an appropriate amp rating and interrupting rating can provide additional protection for the electrical system. Fourthly, evaluate the transformer's impedance. The transformer's impedance affects the fault current levels in the event of a short circuit. A higher impedance transformer will limit the fault current, while a lower impedance transformer will allow for higher fault currents. If the transformer impedance is low, it may be necessary to increase the size of the transformer secondary breaker to accommodate the high fault current levels. Fifthly, consider using a transformer with a higher kilovolt ampere rating and a lower impedance. This can improve the voltage regulation of the electrical system and reduce the impact of motor starting on other loads. However, this option may be more expensive than simply increasing the size of the existing transformer secondary breaker. Sixthly, review the National Electrical Code requirements for motor feeders and branch circuits. The National Electrical Code provides detailed guidelines on the sizing of conductors, overcurrent protection devices, and disconnect switches for motor circuits. Ensuring that the motor feeder and branch circuit comply with all applicable code requirements is essential for safety and reliability. Seventhly, consider the ambient temperature and altitude of the installation. High ambient temperatures and high altitudes can affect the performance of electrical equipment, including transformers and motors. Rating factors may need to be applied to the equipment ratings to account for these environmental conditions. Eighthly, evaluate the condition of the existing electrical equipment. Older equipment may be less efficient and more prone to failure. Upgrading to newer, more efficient equipment can improve the overall performance and reliability of the electrical system. Ninthly, consider the potential for future load growth. If the facility is expected to expand or add new equipment in the future, it is essential to plan for the additional load requirements. Oversizing the transformer and the secondary breaker can provide additional capacity for future growth. Tenthly, consult with a qualified electrical engineer or contractor to perform a comprehensive electrical system study. An electrical system study can identify potential problems and recommend solutions to improve the performance, reliability, and safety of the electrical system. After implementing any changes to the electrical system, it is essential to thoroughly test and commission the system to ensure that it is operating properly. This should include testing the overcurrent protection devices, verifying the voltage and current levels, and performing a load test on the motor.